Yeah. So today I'm going to talk about like 1 minute. It became 1 minute. Yes. So today I'm going to speak about something which is called as soft cores for FPGA, right? And it basically revolves around the free and open source hardware type of system on chip design talk, right? So the idea here is that we can develop in our own processors. We can develop in our own hardware basically, and gradually this is uh, the way to go in days to come, because people would like to develop in their own GPUs, right? Instead of just depending upon GPUs from NVIDIA, AMD, or Intel, because you require a specific application to be run on that GPU, and you require some specific number of accelerating cores, right? So you need not go on with the standard uh, general purpose GPUs for that matter. So keeping that in mind, we are trying to see as to how certain specific soft cores could be used for developing in your own CPU GPU type of a small SoC, right? So with this basic introduction, so let me just start with the agenda. So since this a brief talk, right, I'll be having the first introductory thing about what are the various components of a computer, which we all know, and how is it related to the open source ecosystem, right? And then what would be the levels of representation? How is that ISA is related to the complexity of a processor? People know about it, but actually when you start developing in your own processors, right, how is that the perspective actually changes, and how is that a person has to view it, okay, for developing his or own processors? And then we will talk about basics of something like what are softcore processors, and then MicroWatt is the open power uh, foundations, right? SoftCore, which is released as an open source SoftCore, right? We'll see a brief about what MicroWatt is. Then maybe I'll show you a video which basically talks of how MicroWatt can be basically emulated rather, right, on a FPGA after porting that small MicroWatt core, which would behave as a CPU, and then you can install in your own OS on top of it, and then things like that, right? So this is the overall agenda. So let me just start with this, that when you see the component of a computer and its relation to open source ecosystem, the basic idea is that we would be having a processor, and each of these processors will have actually three things, right? In general, any processor for that matter, you will have the control unit, you will have something which is related to the data manipulation type of stuff, or data path, what people call about, okay, or something related to data, okay. So that portion which relates to data, you have a portion which is control, and then you have the ALU, which basically does all the computations, right? So the basic idea is, when you think of developing a processor, you are actually looking at three different things. One is the data, one is the control, and the third one is the computational aspect of the processor with regards to the data which it is trying to work on, right? And then all of this is actually connected to, right, the memory. Now obviously any data or any program which you write has to come down to the memory of the processor, whether it's a CPU or a GPU. This particular thing always stays, right? And when this happens, you will have these things which you need to care about, which basically are the processor memory interfaces. So you will have to have something wherein you are going to read the data, you are going to write the data. Obviously, you have to have the address generated, and then basically you will have to either enable the read option or the write option or whatever other things you want to do on that, and so on and so forth. So the basic idea is you will be having a processor, you will be having a memory, and apart from these two specific things, right, you will have the IO memory interfaces as to how are you going to give input to the memory and how are you going to get the data out of this memory, right? And this is the whole thing which a computer designer works on, and a person who develops a processor also works on, but they have two different perspectives, right? Both of them have two different perspectives of what is that they are going to view it as, right? So we as people who would basically be trying to develop our own hardware, we have to actually look it at from both the ends, right? We should know how ultimately when a processor is designed, okay, which actually till now was being done by companies like Intel, AMD, right, ARM, NVIDIA, so on and so forth. And when a person starts thinking in that direction, so there is a lot of learning curve which basically exists, right? Because you have on one hand people who have been doing this since decades, right? And then you tell that, okay, everything is open source, you can develop in your own processor. So obviously there has to be a lot of learning which should happen, and there should be a group of people who should be doing it. But effective idea is to develop the ecosystem, right? The open source ecosystem. And open power actually supports this ecosystem, which actually IBM is actually partnering with, and IBM has released its open power core, right, as a soft core, which is basically one of the cores which all the supercomputers in the world use, and that has been open source now. Of course, it's a very, very preliminary, smaller version of that particular ISA, but still, since it has been tested, tried, okay, it is one of the very good cores. So that's what basically is the idea here. Now, let us try to understand it in the context of relating it to when a person actually uses this processor, right? What all does the processor actually undergoes, right? The data manipulation, and how is that it everything happens, right? From the program which a person writes up till it is executed on the logic circuits. So this particular deck tells you about how everything happens, right? This is something which everybody knows, but we will have to go into a very, very deeper details into of all of this to understand and to develop in our own processor, right? I'm not talking of something like a system software simulation type of stuff, but I'm trying to tell you how is it that it's linked to the actual hardware development, right? So here, if you see, there is a high level program which is written in C, or you can talk of it as in Python, or there are other high level programming languages. You take any of them, ultimately you will have to have a compiler or assembler or an interpreter or whatever basically you use based on what type of a language you use here. Ultimately, this particular compiler or an interpreter or an assembler converts it, right, into the machine level language in the end, right? So you get a machine level code here, which is in terms of zeros and ones. Everybody knows about it. And then you basically have to actually interpret it based on the machine on which you want to use it. So there has to be a hardware architecture description, okay, of the machine on which you are going to use this particular machine level language code. And obviously this is dependent upon, right, the instruction set architecture, right? And then since you know that the instruction set architecture uh, is to be used on a specific hardware, okay, now this particular hardware which you are using would be implemented using certain circuits, right? And these circuits, basically you can see the schematic here. So any logical circuit for that matter, if it's a ALU, it will basically have all of these logic circuit implemented, and ultimately your processor is nothing but this, okay, this logic circuit in the end. So anything which you develop at this point has to run on this hardware, and this particular what to say, information passing through at various stages and being transformed from one state, right, to the other state, and then ultimately getting executed is something which you have to link it with the hardware which you are supposed to be using, which basically is something like this, right? So I hope this is clear. Any questions here?
No questions, Professor. Just continue.
Okay, so now, so then let's come to the instruction set architecture, right? And instruction set architecture, when you try to say, okay, we have something like a central processing unit, which basically is a CPU and which is also called as a core, right? And these cores or the processing elements or the processing unit are supposed to execute the instructions, right? And these instructions are supposed to be the CPU's primitive operations or the core's primitive operations. And we all know that these instructions till now, if you are not using parallel computing, would be in a sequential manner, right? So instructions are executed one after the other in sequence. And we also know that each instruction will do some amount of work, which ultimately will end up as a part of a bigger program which needs to be executed. And these instructions are basically certain operations which basically you apply, okay, to the operands, right? And then you can change the sequence of instructions. There can be optimization done of the sequences, so on and so forth. But the idea here is that you will be using certain instructions, and those instructions are the instruction set architecture specifically. Now this ISA changes from the way in which your architecture is designed. It can be a CISC architecture, it can be a RISC architecture, okay? So here we have got various ISAs. We have Intel 86, AMD, ARM, IBM PowerPC, Intel IA64, you have RISC-V, and then you have open power, which is MicroWatt. So you have a specific instruction set architecture, and we are trying to discuss something in relation to the architecture which is called as MicroWatt, which is released by Open Power Consortium, and which actually is a IBM PowerPC core architecture, right? So then, as I told you, that CPUs will belong to various families based on the type of instructions you would be using. They're classified as CISC and RISC. So now let's try to understand, when people started developing these instruction set architectures, early trend, right? You can actually go on adding instructions so that it becomes very easy for people to use CPUs, right? So one of the architecture which was called as wax architecture had an instruction to compute polynomials directly, right? So think of the complexity of that instruction, and think of that particular instruction, if it needs to be implemented using something like a RISC, what would be the size of that program for computing polynomials, okay, or solving polynomial equations, right? But this wax architecture had an instruction which could compute polynomials. So people thought of various ways by giving instructions so that it can help now users who would be using their architecture, right? So keeping this in mind, let us try to now understand how is it linked to the small microwatt core which Open Power Foundation has released. Now let us try to understand it in context of something like RISC. Now RISC philosophy tells you keep the instruction set small and simple in order to build fast hardware. So all of these RISC systems will have very small instruction set. But when you write a program, right, the program would obviously be a bigger program in size as compared to the program which you write it on a CISC processor, because the instruction set would be more in case of CISC, right? And now if that is the case, okay, then how do you actually put in instructions which are required by you? So that is what you as a designer of a processor which you are trying to design actually comes into play, right? So you are a designer, you are going to design your processor. So there is some SoftCore which is released by IBM along with Open Power Foundation. It's a very small core. It has got some limited instructions. You are developing your own processor, so you go on adding instructions, right? And then try to release it as your own core, right? So this is the whole philosophy. Now that basically also means that the RISC compiler is going to generate software which basically will do complicated operations by combining each of these simpler ones, right? So that is how it's going to be thought of as. Okay. Now, what are these SoftCore processors, right? So when you see a motherboard of your CPU, there is an Intel processor or an AMD processor, okay, or an ARM processor, whatever. Okay. So that basic processor is a physical processor. What we are talking of now is a SoftCore processor. And this SoftCore processor is a processor that is implemented entirely in the logic primitives of an FPGA using VHDL. So this means this is a processor which has been developed in pure software VHDL, which basically could be ported onto the FPGA to see, okay, whether your processor is working, and as and on you go on improving upon it. You add instructions, you add your memory, you add everything to it, you can develop in your own SOC, right? So I hope this idea about a SoftCore processor is clear. Okay, so the core processors or the SoftCore processor which we talk about, you can have RISC-V, you can have MicroWatt, you can have so many other SoftCore processors. Each of these processors, they are not having speed or performance characteristic, right, as you get it in a discrete processor. So a SoftCore processor is going to allow a designer to add or subtract peripherals, add or subtract instructions, okay, for developing in your own system on chip with certain ease, right? And then this SoftCore processor is going to offer flexibility for configuring the core for the application for which you are designing that particular processor, right? So using a SOPC solution will offer flexibility outside the FPGA while designing the circuit board. So there are various ways of doing it. We're not going into the details now, but people interested can discuss, and we can do things on that front, right? So now SOPC exists in an FPGA. The pinout is flexible, which gives the board designer almost complete freedom with component placing while meeting the timing constraints. So this is at a different level. As you go into the details, you will try to understand what is SOPC and what is SOC and how is it related to the overall ecosystem of the FPGA. So, but the basic idea is that you should understand what a SoftCore is for the time being, right? So now, as I told you, SoftCore is a FPGA implementation using VHDL. So the Open Power MicroWatt, okay, is an open source SoftCore processor written in VHDL by Anton Blanchard at IBM. It adheres to the PowerISA 3.0 instruction set and can be run on FPGA boards. You can boot Linux out of it, MicroPython out of it, and Zypher out of it. So this is a real-time operating system, which is Zypher, and you can boot Linux, MicroPython, and Zypher out of it. Now, what does it mean? It means that MicroWatt technically is a 64-bit bi-endian scalar integer processor core. So it's a single processor core, okay, which can implement, okay, a subset of the PowerISA 3.0 instruction set. So if you see power processors or power PC, which has a processor, which is a power processor, there is something which is called as PowerISA 3.0 instruction set. So this basically means your power processor or power PC processor has got a set of instructions which it can execute, and this MicroWatt is a subset of the instruction set, which is the actual instruction set which power PC users use for their own application development, right, or when they run in their own programs. Now this MicroWatt is having 32 general purpose resistors, each of 64 bits, since it's a 64-bit processor, and it has got 32 64-bit floating point resistors. So you have 32 general purpose resistor, 32 floating point resistors, and it actually uses Wishbone for memory interface. So the idea here is, when you start developing your processor, you have the processor, let us say in this thing, as the MicroWatt, and then you have this memory, and this needs to have this connection. So there has to be a power memory interface, and this memory interface is actually, okay, uses Wishbone, okay, for the memory interface. And at present there is no memory management unit and no floating point unit, okay. So the idea is, it has got no memory management unit. So you, as a developer, if you are using SoftCore MicroWatt processor to develop in your own processing chip, right, you will have to develop a memory management unit and a floating point unit for actually using it to process some data, okay, and use it as a processor. I hope it is clear till now. Any doubts? Okay. So the idea is that when you want to implement it, right, when you want to implement such thing like a MicroWatt, you will have the fetch, decode, and the execute cycles, which obviously will end as a write back cycle, right? And you have multiply, divide, load, and store operations which you need to do. So you have this fetch, then you have iCache, then fetch 2, then decode 1, decode 2, execute, and write back operation. So this is how actually you basically work with a soft core, which is a MicroWatt soft core, right? Now, when you see this MicroWatt core, and I told you that it is written in VHDL, so there will be so many files. When you go to the GitHub, you can download MicroWatt core and see, and basically try to understand it. All of this is written in VHDL. So you have got decode types, you have got Wishbone types, you have fetch 1, decode 2, then you have this logical.vhdl, you have control.vhdl, then you have execute 1, you have FPU, you have load store, MMU, dcache, divider, rotator, PMU. All of this, right, is in VHDL. So you can actually use it to port it into a FPGA and actually test the functioning of the core, okay? Because FPGA can be reconfigured for developing in your own system on chip or a compute element or whatever, right? So these are certain snapshots of trying to link or actually link the FPGA board to the PC and then you can generate in the bit stream, which basically is a microwatt bit stream here, using certain tools like Xilinx, Vivado, ToolSuite, and so on and so forth. Okay, and then generate a bit stream which actually gets ported onto the FPGA, and you can see that your microwatt core could be used and you could start developing something on it. Okay, so this is how we actually ported the microwatt core onto the FPGA. And then, since it does not have anything, right, on the left hand side of this screen, on the monitor actually, you can see that it is just connected, okay, through a serial communication link to the core, which basically can do certain transfer and receive operations, right? Very simple transfer and receive operations. Yeah, so I suppose, yeah, that's it. These are certain references. I can show you some demo and some snapshot of how basically it will look like. So just let me share something else with you. Give me a sec. Yeah, so if you see this snapshot, this is a snapshot which we took and which basically shows you the same thing which I told you, that we are porting this bit stream, which is a microwatt softcore bit stream, onto this FPGA board, which is the Nexus A7 100T board. And if you see here, on the left side, there is a terminal which tells us that the microwatt core is there in that particular FPGA and it works, right? So this is just only this much. To do many things on that as your processor or the way in which you work on your PC, lot of things needs to be done. But this is a way in which you can start developing your own processor or open source hardware, right? So that is what it means specifically. And ultimately, when you try to design everything using open source tools, there is something wherein you need to start it to be manufactured, right? Or you want to manufacture that board now, or the system on chip ultimately. So you can use various tools, okay, which are there, and then you basically can develop the layout using open source tool again, which is called as Corollius 2. I will show you the snapshot of that particular layout as well, which is something like this. So this is again an open source tool which will help you to develop layout. And if people who have done VHDL Verilog programming, ultimately they know that the layout after optimization has to be done like this, all of these components, everything like this, and then it can be sent to the fab, right, which can basically manufacture your chip designed, whatever you have designed, and something like this, right? So yeah, so I suppose, yeah, I'm done with it. Of course, there is one more video which shows the working of the way in which it is actually booted So maybe I'll show you that. Maybe you'll not get the sound, but you'll be able to see it. I can speak over it. Give me a sec again. So this basically shows you the way in which you actually try to port in MicroWatt onto the FPGA, and this basically shows a MicroPython running there on the MicroWatt core. So the idea is here we can boot in the MicroPython. We have to use GHDL, and we are actually trying to use the PowerPC 64 LE Power 8 glibc actually. Okay, so yeah, so this. This will show all of this, and then there are so many things which if you install this all available freely on the internet on the GitHub. And then we have done a very small hello world program which basically is just a console type of a stuff as I showed you, but we improved upon that and just tried to do a scanf and a printf in C, and that too just very minimal, right? It just takes character, it does not have any other thing in it. So maybe that is what you will see also. So yes, so this link I can share and then you can see it, view it, and let me just fast forward it a bit so that no. So yeah, so this is just like trying to just print in some numbers, right, and the name or something like that by printf, scanf, and a very small C program type of stuff. Yeah, so I'm done, I suppose. Yes.